Hello, my name is Braden Kohler. I am a graduate student at the University of Maine, working under Dr. Barabee, Dr. Lopez-Anito, and Dr. Goupy on Project 210, the implementation of a structural health monitoring system for carbon fiber composite strands in the Penobscot-Narrows Bridge. Now, the United States has been suffering from increasingly aging and decrepit infrastructure systems, with most bridges in the US being over 50 years old. The American Society of Civil Engineers has given the United States bridge systems a grade of C-, citing the age and structural deficiency of these bridges. Given the need to improve the longevity of these structures, new materials are being investigated to improve bridge designs. Carbon fiber composite strands, CFCS, are one of these newer materials that have the similar strength properties of steel. However, unlike their traditional counterparts, they have substantially higher resistance to corrosion. This material shows promise to help strengthen and improve our structures, but whether it is durable enough to compete with steel still needs to be determined. Now, the Penobscot-Narrows Bridge spans between Verona Island and Prospect, Maine, and is a stay cable bridge where a pair, which will be determined as left and right side through the rest of the presentation, of carbon fiber composite strands were installed in 3 different stays, stays 2, 10, and 17. These strands were installed in 2007 and have been monitored at infrequent intervals throughout the bridge's lifespan. The initial system included a variety of instrumentation, including load cells, fiber optic strain sensors, temperature sensing, both internally and externally, and linear variable differential transducers. All of these are pictured in Figure 1 in the bottom left, looking at one of the anchors at each of the stays that have the carbon fiber strands in them. To better understand the durability of these strands, this project presents the installation of a wireless data acquisition system at the bridge to collect real-time continuous data of the carbon fiber composite strand performance. Using a network of wireless nodes and a central base station at the center of the bridge pylon, the sensing network will connect to a central computer and will acquire data continuously while also being remote accessible, as pictured in Figures 2 and 3. The system will be controlled through a combination of the wireless node communication program and a LabVIEW program that merges the wireless and fiber optic data into a single file. It also is presented to have anti-shutdown features so that if we were to lose power at the bridge, the system will restart on its own and collect data on its own, and there's no major fears of losing massive data due to a blackout. Now, to process the continuous data, a transient thermoelastic model was developed in 2014 to use the external temperature as an input to create a time series of the temperature of each individual material inside the stay. This includes the high density polyethylene shielding, the internal air, and the carbon and steel strands inside each stay. Now, using these temperature series, the load of the carbon fiber composite strands can be predicted with this model. Now, it is important to note that the model assumes that the cables do not suffer from any nonlinear effects, such as stress relaxation, creep, or anchor slippage. Therefore, as we look at the data and how the measured data compares to the modeled data, we can determine whether or not we're potentially seeing any of these nonlinear effects. For example, in Figure 4, which has data from the left carbon fiber cable in stay 10B, we can see that over this week in August, that the measured and modeled data, they align pretty well and have relatively similar loads. If we were, again, to see any of these nonlinear effects on the strands, the modeled and measured forces would begin to drift apart. In processing all of the data that we have collected from 2008 up until 2021, the largest drift we have seen is actually at the same stay, 10B, but in the right cable. And that is on the magnitude of about 5% difference between the measured and modeled loads. Now, given the large loads that these strands are subjected to, a 5% change is about 1,250 pounds, but that's out of the 25,000 pounds that the strands are subjected to on a day-to-day basis. Now, as we collect more data at the bridge, we can start to monitor the trends that we see and determine if the strands are indeed behaving abnormally and start to investigate whether or not these are from the nonlinear effects I've mentioned, or if they are performing correctly, or if there's anything else that needs to be investigated. Now, it is also important to note that the model does not completely capture all of the inner workings of the bridge, such as the high thermal mass of the concrete deck. So the long-term data that we can collect with this continuous system will better illustrate the carbon fiber composite strand performance throughout its lifespan of the bridge. Therefore, with this system installed, we can collect data at the bridge 24 hours a day, 7 days a week, 365 days a year, and begin to determine the long-term trends of the carbon fiber composite strands and look to make a durability assessment of this new material. Thank you.